is the first video for 6.4. In this, we're just going to use some properties of the definite integral. We've actually seen these a little bit already, but just to kind of make it more formal. When we are adding two functions and we're trying to integrate those, we can actually split it into two separate integrals using the same bounds, and we can evaluate it separately and then combine those. This works for subtraction as well, addition or subtraction. If we have a constant multiple times a function, we can actually pull that constant out. Same thing with when we find the derivative, the constant just kind of remains there. We can do the same thing with integrals. Okay, so we're going to do a couple examples where we're going to use those properties. I'm just going to zoom in a hair more here. Okay, so this first example, this is where I can kind of use this first idea of splitting this into two separate integrals. So I'm just going to do it like that so you guys can see that illustrated. So I'm going to keep my upper and lower limits of 0 to 1. I'm going to evaluate x squared. And then because it's addition in between, I'm going to keep that. All right, so now to evaluate a definite integral, we know we take the antiderivative and then plug in the upper and lower limits and subtract. That's the fundamental theorem of calculus, part 2. And so the antiderivative of x squared is x cubed, and you guys, x cubed over 3, excuse me. And you guys have seen that vertical line I've used. Your book also kind of uses this notation to show this is the antiderivative we're evaluating between 0 and 1. And then we're going to do the same thing. Antiderivative e to the x is itself. And again, we're evaluating that from 0 to 1. So I'm going to plug in 1. And then I'm going to plug in 0. And I am subtracting there. So that's kind of this first piece. Plus, now we're doing it with e to the x. So e to the first minus e to the 0. Okay. This becomes 1/3 minus 0 plus e minus 1. Let me write that up here. So we've got 1/3 plus e minus 1. So I get e minus 2/3 there. And I'll just leave it like that. Okay, this one we can apply that constant multiple property where I can pull this 3 out and rewrite it like this. And that just maybe makes it easier to recognize because that's a very common antiderivative we use, right? The antiderivative of 1 over x is natural log of absolute value of x. So again, I keep that 3 out front. And again, here's kind of that evaluating notation we've seen. So now I'm going to substitute in e, so natural log of e is positive, so we're good on the absolute value. Same with 1. All right, natural log of e is 1, natural log of 1 is 0, so we've got 3 times 1, which is 3. All right, this one. So we don't have any rules for a division or multiplication at this point. So when we see something like this, we're just going to divide each term. So I'm going to go ahead and go piece by piece. I'm going to divide each of these by 2x. So what's going to happen here is I'm going to get my x cubed and x will be left with x squared, and I'm left with 3 halves. Okay. Negative 6 divided by 2 is negative 3. And then x squared over x is just x. Minus 5 over 2. And then x over x would divide. And then 4 over 2x is going to leave me with 2 over x. Okay, so same thing. I can kind of split these all into separate pieces. So I'm going to do that just so you, again, I can illustrate those properties. So I'm going to pull out all the constants. So this first part, keep my 1 and 2 bounds, okay? And then we got x squared dx minus, pull out that constant multiple, minus, and then this, you guys might see something like this too, with just the dx, that's like 1 dx, okay? And then pull out the 2, and we got 1 over x dx. Okay, so that's like applying those properties to every single piece, pulling out every single constant multiple, okay? And so now we're going to evaluate each of those using the antiderivative. So we've got antiderivative there is x cubed over 3. And we're evaluating between 1 and 2. Antiderivative of x is x squared over 2. And antiderivative of 1 is x. And then antiderivative of 1 over x, natural log, absolute value of x. All right, okay. And so now we are substituting in our upper and lower here. So 2 cubed over 3 is 8/3. 1 cubed over 3, 1/3. Our 3 there. Okay, so 2 squared is 4 over 2, which is 2. 1 squared over 2 is 1/2. 2 plug in, 1 plug in. Here we've got natural log of 2 minus natural log of 1. Okay, a little bit further here, let's see, we've got 7/3. So but my 7, the 3's are going to cancel with that 3, so I'm going to be left with 7/2. 2 minus 1/2 is 3/2. Times 3 is -9/2. -5/2 times 1 is -5/2. And then here I've got 2 natural log of 2, and natural log of 1 is 0. Okay, so, and then I can combine here. Let's see, we've got -2 minus 5 gives us -7/2 plus 2 natural log of 2. All right, so that's just using those properties, you guys. Now we're going to look at another very common integral property. So if I have an interval that I'm finding an integral for, and our interval contains a, b, and c, we can like split this integral into two different integrals as long as c is somewhere in that interval. So this comes in handy with piecewise functions in particular. Excuse me. So we have two different functions, and this is good to check continuity, but also I'll talk about it, I guess, when we get to the second one. So if I were to plug in kind of 10, that breaking point, if I plug in 10 for both of those, I get 100 for both, so it is continuous, meaning I can integrate. So we're looking from 0 to 15, so I'm going to write out the whole thing first. So we've got 0 to 15 of f of x dx. We're going to split that into 0 to 10, and then 10 to 15. So this again is helpful because from 0 to 10, I'm going to use this function. So we've got 0 to 10 x squared dx. And then from 10 to 15, it's a different piece. It's 100. Okay, and so now we can evaluate like we normally do. So antiderivative here is x cubed over 3. We're seeing that one a lot. Evaluated from 0 to 10. And antiderivative of 100 is 100x. And we're evaluating that at 10 and 15. Okay, so let's see, we got 10 cubed is 1,000 over 3 minus 0 plus, let's see, we got 1,500 minus 1,000 is 500. Getting a common denominator, if I want to, would be, what, 1,500? So then we got 2,500 thirds. Okay, and this is our area, and I'm going to add one more piece here, you guys. I'm going to call this, we're just going to do units squared, because they're specifically asking us to find the area under the graph of this piecewise function. Okay, now, another one, we just have 4 different pieces here. Now, you might notice, hey, this one isn't continuous. It has some jump discontinuities, so can we actually integrate this? The answer is yes. So I'm going to have you guys write this down. So if f is bounded, sorry, you can't read that, is bounded and at most has a finite, meaning we can count the number, a finite number of points of discontinuity on an interval, then our integral from a to b of f of x dx exists. So we can integrate if there are finite jump discontinuities. So the other thing is kind of to interpret, well, then when can I not? It's when we have an infinite discontinuity. So that's something like a vertical asymptote within our interval. Okay. All right. So we're going to approach this the same way we did number 4. We have all these pieces. Now you might notice this piece too, right? Still, we're going to look at from 1 to 0, negative 1 to 0, 0 to 2, and then my next interval is going to be 2 to 4, because there's not 2 different bounds in this one, so we're just going to use these 3. So I'm going to evaluate from negative 1 to 4, so we've got negative 1 to 0 for the first part, and we're using e to the x. Then we're going to do from 0 to 2 for x plus 3. And then lastly, we're going to do from 2 to 4 and use that last piece, negative 2x plus 9 dx. Okay? All right, so now we are evaluating the antiderivatives. The antiderivative there is x squared over 2 plus 3x. And antiderivative there is going to be negative x squared plus 9x. All right, so here I got e to the 0 plus e to the negative 1, which is 1 over e. Oh, sorry, that should be minus. Okay, plus, let's see, we got 2 squared is 4 over 2. It's 2 plus 3 times 2 is 8. Plug in 0 for both those, we get 0. 4 here, negative 4 squared is negative 16. Plus 36 is 20. Plug in 2. Negative 4 plus 18 is 14. All right, and we simplify all that, you guys. This is just 1. Add all those constants, and we do get 15. And then I'm just going to leave the minus 1 over e in that form. Okay, we've got one last example. Okay, in this one, you guys, this is a theorem involving the bound. So it's kind of stating that our integral or our area underneath a curve has to be between a certain value on a low end and a certain value of the high end. So we're going to use this little m to denote the absolute minimum of a function and the capital M to designate the absolute max. And then on our interval, this will always be true. The absolute minimum times the difference in our interval will be the lower bound, and then our absolute maximum times the interval is going to be our upper bound times the difference in our interval. Okay, so let's do that. We're asked to find the upper and lower bounds for the area of the graph of sine of x from 0 to pi. So let's use what we already know about sine of x. So if I'm looking at the graph of sine of x from 0 to pi, it just looks like this, right? It's all positive. Its highest point, right, occurs at pi over 2, and my max there is 1. So we already know, just from our basic information of our sine graph, we know we have an absolute max at, I'm going to write it as an order pair. So we've got pi over 2 is the x coordinate, 1 is the y value. And we have absolute min. We have 2 of them because it occurs at 0 and pi. So 0, 0, and pi 0. Okay, so remember our m, our capital M, is going to represent the absolute max. We're going to use the y value for that. And then our absolute min, both of these have a y value of 0. Okay, And then b minus a, right, is this piece. That's our interval. So our interval is from 0 to pi. So pi minus 0 is just pi. Okay, so to write it in this way, we have little m, which is 0, times b minus a, which is pi, less than or equal to our integral from 0 to pi of sine x dx has to be less than or equal to our max, absolute max, times our b minus a, which was pi. Sorry, our absolute max was 1. I can plug that in. Okay, and so 0 is less than or equal to our integral from 0 to pi of sine x dx, which is less than or equal to pi. So this one actually matches our bounds. That's not always going to be the case, you guys. This just kind of happens in this setting. But that's how we find that lower bound and upper bound. So our absolute min times the difference in our interval, and then our upper bound is the absolute max times the difference in our interval. Okay, now it says find the actual area. So now that just means let's evaluate this function, this integral, okay? So I'm going to do what I've been doing. Antiderivative of sine is negative cosine, and we're going to evaluate that from 0 to pi. So we've got negative cosine of pi minus negative cosine of 0. So we got negative 1 plus 1 gives us an area of 2 square units under the graph. All right, guys, that is it for this video. Thanks for watching.